Today our topic of discussion is Support Vector Regression, that is SVR, which is invented by Vladimir Vapnik and his colleagues. Now look at this diagram. So we have two plots over here. In order to compare SVR with the simple linear regression, it will really help you to understand by using this diagram. So in the left, we have some random dots. Same thing is copied in the right in order to make them identical so that I could compare these two diagrams. So in the left, we have applied simple linear regression with a method which is known as ordinary least square. So here we have to understand SVR with respect to simple linear regression. Now, here we are trying to minimize the distance between the actual values, which is known as y and y hat. So, we are taking the difference of each point and square them. And here our aim is to minimize this. So, that's why we are using this formula. So it is a simple least square regression method. So essentially we are here minimizing the error and we have a line over here, and this line is known as the regression line. And our main intention is to find out the distances of each and every point from this regression line, square them up and find the minimum value. So now here today our topic of discussion is support vector regression, which is at the right side. Now how does this support vector regression work? It is very essential to understand. Now in this diagram you will see a particular tube. This yellow one is the tube. So instead of a single line that I have showed over here, here we have used the regression line in the middle of this tube. So now we have to understand first what is the purpose of this tube. So this tube has a width. So this is the width of the tube, which is measured vertically to this x2 axis. So they are perpendicular to this tube. This tube is known as epsilon insensitive tube. Now we have to understand what is the meaning of this epsilon insensitive tube, where epsilon is the width which is measured vertically with respect to x2 axis. So here epsilon insensitive tube means at any point in the data set, which is depicted here by dot, that falls inside the tube, they will be disregarding the error. So basically, it is a margin of error that we are allowing our model to have and not care about any error inside the tube. Whichever error is visible inside the tube, we are not going to care about it. So any discrepancy or any distance between the points inside the tube and the regression line, we don't care about the error. So this is the key behind the SVR. So SVR gives little bit of buffer in our model. And at the same time, the points we are having outside this epsilon insensitive tubes, for them we do care about the error. So try to understand the most important point. In this simple linear regression method, we have a regression line and we are finding the distance from each and every point, means how far they are from this regression line, and we are squaring them up and minimizing them. But in case of SVR, what we are doing here, along with the regression line, we are creating one tube, yellow colored tube, and try to understand in this tube whichever data points are there, they have some error. But here the concept of SVR is we are not going to care about this error. So we can ignore them. But whichever points falls outside this epsilon insensitive tube, we only care about the error margin of these points. So this is the main concept that you have to understand. So that's why I'm talking about that SVR gives us a little bit of buffer in our model. It is allowing some sort of marginal error. But here we are trying to find out the error and trying to minimize them directly from the regression line. So that is the basic difference. So here in case of SVR, the point is the error will be measured among the distance between the tube and the points. So here which one is the error? The point which is outside the tube and the distance from this point from the tube. Whereas here the error means the distance from the regression line, means the distance between the point and the regression line. So this is another key difference. And here the main thing is we are not considering the error from the trend line. And now we have to understand what is this point are known as, because the points which lies outside the tube, we are only caring about the error of these points. So the point which falls below this tube is known as z star, and the point which falls outside the tube but in the upper side, it is known as z. So this z factors are known as slack variables. So here my point is SVR will only consider the distance of the slack variables from the tube as an error. So we care about the slack variable distance only in case of SVR. So in compared to the ordinary least square regression method, so we also have a formula for support vector regression where each time we are going to minimize this factor. So here considering the slack variable and their distance is important. So SVR is definitely a supervised learning algorithm and which is used to predict the discrete values. In the previous class I have explained that whenever I'm talking about regression, they will follow some discrete values. So in this case, since SVR is a supervised learning algorithm and they used to predict some discrete values, so SVR uses simple principle of support vector machine. So here the basic idea behind SVR is to find the best fit line. So it is the objective of any other regression method also. We have to find out the best fit line for our data points. So in SVR, the best fit line is also known as hyperplane that has the maximum number of points. So in this case, this one is the hyperplane that you can consider where you are trying to find out the hyperplane that has the maximum number of points. So unlike other regression models that try to minimize the error between the real and the predicted value, the SVR tries to fit the best line within the threshold value. So that thing you have to understand. Threshold value is the distance between the hyperplane and the boundary line. So this is the threshold. Hyperplane and the boundary line and their distance. So linear SVR provides a faster implementation than SVR, but only it considers a linear kernel. So here I'm talking about the model that produced by the support vector regression depends only on the subset of the training data set. Because whichever cost function it is using, this cost function simply ignores the samples whose prediction is close to their target. So this is the main thing that you have to remember. However, efficiently any points on this plot are vectors. So in case of SVR, you have to understand one more point. Whatever point you are finding over here, each and every points are known as vectors in 2D space. And the points that are outside the tube, which is also known as slack variables, they are actually the support vectors. So why they are vectors? Because they are points. But why they are support vectors, the points which exist outside the tube? This thing you have to understand. So basically, they are known as support vectors because they are supporting the structure formation of the tube. Means position of these lag variables will determine what will be the structure of this yellow tube. So that's why they are known as supporting vectors. So here our main intention is to find out one SVR model that can fit into our given data set. So this thing we are going to design in R today. So I'm just giving you a very short recap, that is what are the main intention in case of support vector regression. 3 points you have to remember. First, we do not use any regression line alone. Second, apart from this regression line, we will create one tube. The structure of this tube is controlled by the slag variables. Slag variables means the point which exists outside the tube. Then we have to remember this slag variables are contributing for formation of this particular tube. So as a result, they are also considered as support vectors. And meaning of vector over here is whichever point we are visualizing in this 2D space, they are known as vectors. And also SVR is little bit different from other regression algorithms because they are not calculating the error straight away from the regression line to the point. They are calculating the error, which is a distance between the boundary of this tube and the slag variables. So these are the points that you have to remember. Now we will move on to the coding section, how we can code this thing and what is the concept of kernel that I was talking about, what is the concept of training data set and subset of the training data set that we have to understand via coding. Now here try to understand the first step. What we have to do, we have to understand. So in case of support vector machine, we know that it is a supervised learning method and support vector machine can be used for regression and classification problems. So here today we are using support vector machine for regression. That's why it is known as SVR. So this is the first point. Then the second point that you have to understand, that here we have one library E1071. This is a package in R which provides SVM function to build support vector machine model to apply regression. That is, my point is, actually today our topic is support vector machine regression. So since SVM function is used for both the purpose for regression and classification, so here we are using one specific library E1071. This library provides this SVM function to build a support vector machine. So whenever you try to write this code first time in your machine, either you have to write this code install.package and then within single quotes E1071. Either you have to write this code or you can do one thing, go to the package section, go to the install section and then just install the package E1071 and then click on install. So it will be installed. So immediately after installing this package, then only you can write this library. So this point you have to remember. So here in one word, my point is whenever you are going to define any support vector machine related activity, whether it is a regression or classification, you need to import this package and you have to use this library. This is the point. Now, what are the steps that we are going to do in this code? The first step is we have to prepare our data set. So what do you mean by preparing the data set? I will explain it. Now, what is the next step? The next step is we have to design one model, that fitting the model and predicting the test data. So that is the second intention. And third intention is we have to find out the accuracy. So accuracy checking part. So we have just 3 parts in this code. So now let's see how to import the data set. So this is how we can import the data set. So I'm importing a CSV file by using read.csv command and storing it into the frame which is known as dataset. So you can give any name. So dataset is the name of the frame. One thing we have to remember that whenever we are going to import any data set, the first thing that we have to do, we have to find out the location of the data, and then we have to set this as the current working directory. So then only we can use this data. So this is the point you have to remember. Afterwards, we have to process the data. Now, after executing this one, now we have to process our data. So from where should I get this data? This is the important point. So this is how we will process the data. But first thing we have to understand how our data set will look like. So this is our actual data set which has position, level and salary. See, we have here 3 columns. So whenever we are importing this CSV file, so we are importing the 3 columns. Now processing the data set means here we are going to predict on the basis of the level. So what we will do, it is written as 2:3. So I will keep here this 2 columns only, this level and salary, 2:3. And you have to understand in R the indexing starts from 1. So 1, 2 and 3. So these are the 3 columns. So I will keep this second and third column. So that's why I'm processing this data in this manner. So after processing this data, so you have to do one thing, you have to check for the missing values. So we are importing the data, we are processing the data, and then we are checking the missing value. So how to check the missing value? We know that is there exist any not applicable value or NA value in our dataset or not. So I will write is.na, and here the data set is stored in this variable data set, and here I am checking in the level column is there exist any missing value or not. Similarly, I can check for other column also. So here check, here the output we have got is 0. So it means we have no missing value. So it is visible that in level column we have no missing value. So similarly, we can also check we have any missing value in the salary column also or not. So in this case, at this point, we have to write salary instead of level. So as we know that there is no missing value, so I'm skipping this one. Now we have to come into the most important part, that we have talked about the package installation and using this library E1071. Now the most important line is this one that I'm going to explain. So after using E1071 library, we have to start defining the SVR regression. Now see this regressor variable. So in this regressor variable, what I have done, I have created one function, and the function name is known as SVM, Support Vector Machine. And here the first argument in this function is formula. And see, in this formula, I have written that formula equal to salary. Here, what is the meaning of salary? You have to understand. So here I am defining that this SVM function uses the first argument, which is formula. And here we are writing the dependent variable, which is salary for our data set. And we have used one tilde symbol. And we have dot over here. Now what is the meaning of dot? Dot represents all the dependent variable in the dataset. So whenever I'm talking about this dataset, I have explained in the previous class, we have x versus y. So here y means our dependent variable, means salary varies on the basis of level. So in this case, in the left hand side of the tilde sign, we have to write the dependent variable. And in the right hand side, we have to write the independent variable. But here the dot means I am using all the dependent variables. So dot means all. Now we have the second argument as data. So here our data is stored into the frame which is known as dataset. So I'm just using the frame name over here. Now, the most significant parameter which is known as type. This type argument is very important. It will define for what purpose we are using the SVM model, for classification or for regression. So here I have written that EPS regression. So this term is used whenever we are going to use our SVM model for regression. And here try to understand, if we want to use SVM model for classification, so in this place instead of EPS-regression we have to write C-classification. So basically, depending on the purpose, what we are going to do with this SVM function, we will change this type. And here we have one concept of kernel. So here kernel equal to radial means we are using one nonlinear regression model, and here we are using the radial basis kernel. So what is the meaning of this? I am explaining. But here try to understand, while writing this term EPS underscore regression, you have to use this single quote in order to avoid any error. So now here whichever kernel we are using, instead of this kernel means radial basis kernel, sometimes other kernels like Gaussian kernels is also used. So this type of kernels are default one. So Gaussian kernels is the default kernel, so that we can use, or else you can change the kernel type depending on the situation. So what is this kernel is all about? See, the kernel means all the kernel based methods are based on the distance. So in the starting of this class, I have explained that we are concerned about the distance of the points, that is the data points, how far they are from the regression line or how far they are from the tube. So in this case, we are talking about SVM, support vector machine based regression. So here we are finding the distance from the points, from the regression line and from the tube. So here this is a non-linear kernel, but what happens if we use some linear kernel? So the concept of linear kernel means linear kernel deals with the cost function, say C. This cost implies the number of misclassification cost on training data. And here try to understand, if the C value is large, it gives you the low bias and high variance. Now here the point is, each time whenever we are using some mechanism or we are using some model, here we are trying to minimize some cost. So this one. So cost means you can say that the distance. But this cost is associated with distance. So that's why this cost is associated with kernel. Now we have to understand, if the value of this cost is large, means in case of classification, we can say that we have large misclassification in case of training data. Within the training data, we have large misclassification, which will result in low bias and high variance. Now we have to understand these two terms. What do you mean by bias and what do you mean by variance? So here the bias means the difference between the average prediction of our model and the correct value which we are trying to predict. So this difference is known as bias. And now what is this variance is all about? So variance is the variability of the model prediction for a given data point or a value which tells us the spread of our data. So it is concerned about the spread of our data. So here my point is, if the cost function is large, then this will give you low bias and high variance. And now if you have very small c, if the cost is very small, then you will get high bias and lower variance. So basically here the small c makes the cost of misclassification low, means it will allow more of them for the sake of wider cushion. So whenever your cost is high, means the misclassification is high, thus it is forcing the algorithm to explain the input data in more stricter manner. So here you have to consider two cases, high cost and low cost. If you have high cost, it means we are forcing to learn our model to read the training data in a very strict manner. So which will sometimes result in overfitting, which is not good for our model. But if we have very low cost, then at this point of time, our model will get too loose in case of understanding the underlying behavior of the model. So here our goal is to find a balance between not too strict and not too loose behavior. So that's why I will explain this concept, that is adjusting this bias and variance which is dependent on the cost, which is in turns dependent on the kernel, is very important. And designing a good model does not mean that we have to minimize the cost. Always we have to find out an average cost that will give us a balance between a strict and not so loose learning outcomes. So this is the main thing you have to understand. Now if nonlinear kernel is used, so in our case we have used nonlinear kernel which is known as radial basis kernel. Here two parameters are used for fine tuning. One is cost and one is gamma. So what you have to understand, whenever I am talking about linear kernel, then we have to only concern about the cost. However, whenever we are talking about non-linear kernel, such as radial basis kernel, here we have two parameters, cost and gamma. So what is cost? I have explained that. Now what is gamma? So this gamma explains how far the influence of a single training example reaches. Means when the gamma is very small, the model is too constraints and cannot capture the complexity, or you can say the shape of the data. So too low gamma means the shape of the data or the behavior of the data, it will not be recognized by the model what we are using. So instead of this radial basis kernel, you can also use polynomial kernel. In case of polynomial kernel, then we have three parameters. The first parameter is the degree of the polynomial. The second one is the scale, and third one is the cost. So you can say that cost is common among all the kernels, but today we are learning support vector regression. So in case of support vector regression tuning parameter, so we will use two factors. One is epsilon and another one is the cost, that is C. So now if you look at this diagram, so this is the epsilon. Epsilon means the distance, means it is the threshold value, you can say that, which is drawn vertically with this x2 line that I have explained. So we have two tuning parameters, epsilon and the cost. These two things we have to remember. So this is the very basic concept of kernel.